So one is on structural connectivity and the second one is on MRE, elastography. Yes, so then let's start with structural connectivity. So maybe this is very well known by this audience, but yeah, this generic slide for like putting everything into context. So then it's connectomics. So then there are like two types of connectomics. One is try to map the physical connections between the different regions in the gray matter. And then for that, you use diffusion MRI. But as we just heard from the previous talk, so then you can also have functional connectivity and do very fancy stuff, as you heard, with fMRI or resistive fMRI. So the main difference is that of course, you need maybe a parcellation of the brain, and then you need to have like this connectivity using diffusion, and then you create your connectivity graph, and then you can do the same with fMRI. But and then both are complementary. You need both. It's not that you're like doing one and then the other is not relevant, but usually you do both. But in our group, we are mostly focusing on structural connectivity, not too much on functional. So my talk will be working on describing more the diffusion part. Yes. So let's see how's the pipeline for structural connectivity. First, you need to acquire your diffusion data, and then the next step is to compute tractography. And then once you have the tractography, then you have maybe a parcellation, and then you create this connectivity map. And then after that, you can do different analysis using graph theory or whatever you like. Yeah, that's fine, but there are some issues, of course. The main issue, there are issues at different levels. So there are issues at the tractography level, which is actually the focus of this talk, is that we are not sure that the tractograms that we are getting with our methods are the correct ones, because we don't have ground truth to compare to, which is a big issue. And then has been shown that most of the streamlines you generate with tractography are false positives. And you have also a problem with redundant streamlines, and you also have like problems of equivalence. I will introduce that later. For the connectivity analysis, you have also other stuff, other issues that I will not talk to in this talk. But for example, you have to define thresholdings. It's not standard the way to do it, because you don't have ground truth again. We don't really know which tractogram measurements are the most appropriate to create the graph. You have also problems of different regions of different sizes. So then you need to come up with a good way to normalize the creation of the graph. And then you have also thousands of different parcellations, which is the best one. So it's a problem. And then you don't have enough subjects, and then you can maybe kill the statistical power. And then you have graph theory or data-driven approaches. So what is best is an open question. So, but I will talk more on the tractography issues in this talk. But first, let's revise a little bit how what is tractography? So the idea is that you have first your acquired data, diffusion data, and then this data is diffusion weighted in MRI, which the idea is that in every voxel you measure the probability of water molecules to move in a specific direction. And in white matter, then you know that this is anisotropic. So then with this information, you can create some orientation distribution functions that tells you the most probable directions for the water molecule that will be then aligned to the axons in the white matter. Once you have that, then you can start doing the tractography. So the first thing is that even if you are in a certain specific point in the white matter, you need to predict the next position in the neural fiber. And then you can just go on and then start from, let's say, one part of the gray matter, just go little by little until you end up in the other side of the brain in another region. And once you have this completed, this is called a streamline. And then you just repeat this several times. Several is millions of times until you get the tractogram. Great. So, but of course, you have a lot of possible sources of errors here. So, for example, the direction prediction. So then you have an image that is the resolution usually is around 2 millimeters, and then you are talking about fiber bundles that are, or the axons, the diameter is in the range of micrometers. So of course you will have a lot of errors there, and then you have problems when you have fanning or kissing fibers, and so on. So it's a difficult problem. So then one idea that people have tried to use is to do tractogram filtering. So it has been shown that most of the tractogram methods have issues with false positives and also redundant streamlines. So then, in a way, you need to do filtering before doing any further analysis for structural connectivity. So then you can see here more or less the idea. So maybe because of many reasons, you can get these red, very crazy paths that doesn't make sense with the anatomy. So these are the implausibles. And then you maybe have one that it's okay with respect to the anatomy, what you would expect. But then the problem is also that since the method do the similar approach several times, you can end up with very similar streamlines, these redundants. And then this is a problem, because then you can destroy your statistics in when you're creating your graph. Let's see. Yeah, this is a way to show it that the problem of redundancy. So let's assume that the first balloon is the ground truth. And then since you are repeating this tractography thing many times, you will expect that, okay, it's fine, because then you are like getting way more streamlines than needed, but it's like homogeneous. But in reality, it's not. It's more like the third one, because you are getting more streamlines in some regions and less streamlines in other regions. So then if you would like to compare the first and the third, you will have a lot of issues, and then maybe you'll have bad statistics. So then maybe the conclusions you get are not true. So then what we have been doing here is to create new methods for estimating these redundants. So we developed a method that we call it randomized tractogram filtering. So there are two very good methods for filtering. One is called SIFT, and another is commit. Is maybe the two most used methods for tractogram filtering. The problem of this method is that what we realized is that we started with a very big set of streamlines. We usually go for 10 million, and then we just run, let's say, SIFT or commit, doesn't matter. And then the classification is binary. So this is good and this is bad. What we found is that what if we just take a subset of these 10 million, let's say 1 million, and then we run it several times. So different sets. So if we do that, so we found that this very same streamline sometimes is accepted, sometimes it's not accepted. And that makes sense because then it depends on the context, on the other regions, on the other streamlines that are like selected for this specific run of filtering. And so that difference is given just because you have. So if one streamline is faulty, is wrong, so it will be wrong regardless of the context. But if the streamline is redundant, sometimes will be accepted and sometimes will be rejected. So then we just run this commit or sift several times with different sizes of the subsets, and then we compute this acceptance rate. So if the streamline is correct, so it should be accepted all the time, no matter what. And the opposite also for the implausible group, that is like the faulty ones. And then something in between is mostly redundant or maybe some errors in the filtering as well. So this is very good. There is a big issue of this method, is that we were using ACP data for this study, and then running all these filtering runs takes forever. So one subject took around 1 week. So this is not really useful for like people working on neuroscience. So we trained a neural network that I think is super basic. It's actually this one. It's nothing, and then we got an accuracy of 90%. So of course it's not perfect, but maybe good enough for running this in a clinical study or clinical studies. Okay, so this is what we found. For example, just to visualize this, so we depending on the number of streamlines that we consider like correct or incorrect, you will see differences here. And as you can imagine, then the statistics will be different downstream. We use some other techniques more from statistics, and we found that around 50% of the streamlines were in this inconclusive group in this study, and then from this 50%, like between 10 and 25%, we are very sure that are redundant. So the other says maybe some issues with the tractogram filtering procedure. Yeah. So the main message of this is that redundancy is important and has to be taken into account. Good. So then another issue that we found is that this problem of rotational equivariance in tractography. So here you see like this is a phantom diffusion MRI, and there are like more or less standard tractography methods. For example, this one from MRTrix, and what this experiment was kind of simple, was just to rotate the input and try to get tractography. So to see if the rotation will affect the estimation of connectivity. As you can see, MRTrix is kind of consistent. It doesn't really change much with these rotations. But there are like new methods that are very promising based on deep learning. And then we found that they have a lot of issues, as you can see here. So this is one method that uses reinforcement learning. And depending on the angle, so that you will see fewer streamlines in some regions. So then, depending on the angle of the data, then you get different results, which is a problem. So then, in this project, we took this method and then make some adaptations to make it rotational equivalent, as you can see here at the bottom here. So reinforcement learning. So then the idea is that we use we need to predict, given this point, we need to predict the next position of the streamline. And for that, we use this reinforcement learning approach, in which you use the information from the neighborhood to and the agent. The idea of the agent is to predict the next position. I will not go into the details of this architecture, but the main problem that we found is actually here in the neural networks that are like in these places, here and here, that they were not equivalent. So what we did was just to replace them with something that is rotational equivalent. So that we use a transformer that is like a method from deep learning, and then this is specifically for SE3 equivalence. Actually, we don't need SE3, we need SO3. But this is more general, so this was okay. And these are the results. So if we just apply this change, so then we can see here that the error, this is the error, the angular error of this stepwise prediction. So it's with training, then it goes down a little bit to, let's say, 2% to the 2% of the deviation of the vector. But if we just use this SO equivalent version, then the error is almost zero. And so you can think that 2% is not that much, but the problem is this is just one step, and then you have to do a lot of steps to go to the other side. So then everything is accumulating. So here's another experiment here. So then we just generate different rotations. So then this is the rotation. No rotation is this point here. And then we just generate a lot of different rotations. So every point here is a different rotation. And the idea is that this score should be homogeneous, should have the same like color, let's say. So here's the original method, and then here is way more homogeneous. So of course it's not perfect, but yeah, it's way better than this. Good. Yes. And this is like the same, but yeah, more visualizations here. So here you see that here is more tends to give the same result more or less. Well, here it changes a lot, especially, for example, if you compare this and this. So you have way more streamlines in this case compared to this one for the original method. Yes. After that, then it's just to do different analysis. So we have different projects now, and we just use graph CNS, for example, for classification, regression, etc. So we are now still on manuscript, but the idea was to use the disease as a way to evaluate, since we don't have a ground truth, the idea was to use the disease as a way to evaluate the quality of tractograms. So here the idea was to use Alzheimer's or Parkinson's, and then classify the graphs after tractography, and then see the impact of filtering after if you do filtering or not, and then see if you can classify the patients in a better way. So from our results, preliminary results, it works for Alzheimer's. So without filtering, so then the classification score is around 80%, and then after filtering you go to 85, so you are gaining. But in Parkinson's, it was surprisingly not too useful, because it doesn't matter if it's filtering or not filtering, it's always like around 50%, so it's useless. And our hypothesis is maybe that Parkinson's is a more heterogeneous disease. So yeah, but still work in progress. Good. So then that was the first part. I will move on to MRE. That is very exciting for us. It's a big project that we are running now. So first, I wanted to introduce a little bit the technique. So the idea is that you are in the scanner, and then you put a pillow that is behind the head here. And then this is connected to a pneumatic pump that is synchronized with the scanner. So then basically you are vibrating your brain, and then you are acquiring this vibration with the MRI. And this is what you get, which is interesting, but is maybe not too useful. It's more useful to get mechanical properties of the brain after some post-processing. So far, we are the only site in Sweden with this technique. For that, then, as I said, so you need a pillow, and then it's very gentle, so it's like a few micrometers, and then the is high frequency. So then the feeling is a little bit like these electrical toothbrushes, maybe a little bit more, maybe you can say. Some of the people here have tried that. Yes. And then you need to synchronize your scanner with this vibration. So you do different acquisition at different phases between the waves and the acquired image. And then the next step is to do this inversion algorithm. That is to go from this wave field to mechanics. So for that, there are like different approaches, and then this is very nice. I think this is from a book. So then you have like, mostly two parameters. One is elasticity, and the other is viscosity. So then you can see here the extreme values here: spring, rubber, marshmallow, jelly, and then I have a collaboration with a group in mechanics at KTH, and then they are very interested in the muscles, and it's very tricky because then if you just span your muscles, then it becomes very stiff. So then they have to. It's a problem. You want to compare patients and controls because you have to standardize very very much the way you acquire the data. Otherwise, the bodies will be crazy. This is not a big issue for brain, unfortunately. And usually in brain, elasticity goes down and viscosity goes down depending on the type of disease. Yep. So we are running different projects here, one on Parkinson's, Alzheimer's and aging with Gregoria that you will maybe hear later this week. More about this, maybe. And children, adolescents, and MS will start soon. These are some like preliminary results for Parkinson's. So then age, softens the brain. And then with Parkinson's is softens even further. Actually, this was shown in previous papers, but it was nice to see that in our scanner as well. And then you see that it is also consistent in different regions of the brain that are relevant for Parkinson. And then you can see here the difference between children and these Parkinson's. So this is the average stiffness for let's say old people. So these are the healthy cohort of the Parkinson's that are 50 years old or older. And these are the children that are at most 13. So then you see that the children's brains are way stiffer. Yeah, this is the same, but in another plane. And then, of course, here you can see that is way softer also the brains of the patients. I will not say much about normalization at AD because you will have Gregoria later this week. But it's kind of okay. That's a pity. Okay, so then stiffness is also reduced in older age, so it's the same trend more or less, and also it is more severe with the disease. But something that is very interesting that she found is that there are like some regions in the brain that are have higher stiffness for people that are very good at some cognitive tasks. So it was nice, I think. Yes. Yeah, so that's fine. But we wanted to know why is it that the stiffness is decreased? And what we found in the literature is that very little is known. So our strategy was to have a very, very long protocols to understand a little bit more what is happening with the mechanics. So we added at all studies this multidimensional diffusion that I will mention a little bit later, QSM that is for iron content for the aging and Parkinson's, neuromyelin that is very specific for Parkinson's as well, diffusion because I like diffusion as I mentioned. Functional MRI is only Gregoria because she likes functional a lot. The castle that is perfusion, and also we have we started a project on cancer, and then for that we also acquired something that is called myelin water imaging. Multidimensional diffusion. It's a nice technique that was actually developed in Lund. So there are people from Lund here, so that's nice. So it can be seen like an advanced diffusion MRI. So in normal MRI, diffusion MRI, you just acquire V vectors and V values. Maybe the people who are familiar with diffusion. Here you have an extra acquisition that is called spherical B tensor encoding. And then with that you get way more information from what is happening in the microstructural properties in the voxel. So in standard diffusion you get FA and fractional anisotropy and mean diffusivity, for example. With this Moody, you can have other stuff like, for example, micro FA or the variance of MD and other stuff as well, which are very relevant for our projects. So you can see here differences. So then if you have a low variance here of MD, and then this is a low MD, so then you can see that all circles here are kind of similar. And here are big bubbles that are similar. But if the variance is bigger, so then you have, let's say, compartments that are of different sizes here and here as well. And this is the same for FA. So then if you have high FA and high micro FA, so then you have this configuration. And here, since you have here fibers in different orientations, the FA will go down, but not the micro FA, which is a good thing. And then the same thing for low FA. Good. So we, the first thing we did was to correlate these Moody parameters with MRE. So you can see here, this is G star is the stiffness, and this is the viscosity. So then here, that means that these two are correlated, but there are like some that are also very correlated. So for example, this one was very much correlated. Here, FA a little bit, but not that much, and so on. So basically, these two columns are the most interesting ones. Sorry that it was very blurry for QSM here, but it was not super interesting what we found. That is because the level of iron is not super relevant for mechanics, but diffusion is important. Yes, and then we have a project that is, yeah, we have some results a little bit. This is actually Sarah. So the idea is to get more information inside the voxel, because the problem of MRI is that the voxels are very big, is 3 millimeters. And then we would like to have more information inside the voxel. So what the idea was to use actually mostly Moody to get more parameters inside the voxel. So how to do that? And yeah, we have two objects. One is this one, and then the other one is to do something that is called virtual MRE. That is given Moody to create a finite element model. And then do this virtual MRE, which means that you would like to predict stiffness just from diffusion, from Moody. Why this is interesting? Because then in this way you would not need to have this pneumatic pump, which is very expensive and cumbersome to set up. So if you have a model that given Moody, you can get estimations of stiffness, then you will be able to install this in any scanner in any part of the world, I guess. So this is something that we are working on with Sarah. So maybe in next meeting we'll show more results on that. Then inversion, I said that that was the most important part, I would say, from MRE, just to go from raw data to stiffness and viscosity. And then it's a difficult problem. And then there are different alternatives. Most of people, they use something that is called direct inversion, that you need to do a lot of assumptions to make it quick. And then it's actually used clinically for the liver. we get estimation of stiffness and viscosity from the scanner directly using kind of the same method. So it's like maybe 1 minute, so it's fine. But it's not too accurate. So then there are other methods that use FEM because you need to solve this PDE. Of course, they are more reliable, but in some cases it can take hours. And then AI-based are methods that are now we're trying to come up with good methods for that as well. Yes, so then this idea, actually this is not our work, but here this group, what they do is just to simulate a lot of patches with stiffness, and then they do simulation, and then they just train a neural network to get the ground truth that they simulated, and they add noise or something. The problem is that the going from true stiffness to wave simulation is expensive if you want to do it the right way. So you are not really saving that much time. Another strategy is to use AI to speed up the computations. So this is something that we did with Christopher. So then the idea was just to have like a basic neural network. So then the input will be, of course, the MRE data, and we added also T1 and FA at that time. And then what we could see is that, which was good news for us, is that just using T1 is you cannot really predict mechanics from T1. So you actually need something. So FA is related to diffusion, so it was kind of okay, but maybe not enough. So that was some time ago. So then we found that Moody is way better for this prediction. Another strategy is to use this virtual MRE. So then we found that good correlation between stiffness and Moody. The only problem that we found so far is that these correlations are very dependent on the side in the brain. So in some regions it's good, in some regions, you need to refine it a little bit more. And then you can use this Moody as an input to generate stiffness, and this is what we have so far. Still work in progress. And another strategy that is very attractive for us is use something that is called physics-informed neural networks. The idea is that we have the PD, we know the wave propagation equations, and we know that machine learning is very good. But PINS is very nice because it combines both. So the idea is to use machine learning, but also include this knowledge of the PDs that we know. So we did some work with some master students, and then actually it works. It has some issues. The main issue is that we wanted to reduce the computations, and it's not really happening with PINS so far. And also we have to retrain the network all the time. So it's not like usually in machine learning, you train your model and you apply this model to other images. Here is different. You need to retrain all the time with new images, which means that it will be time consuming. But this is ongoing, so we'll see. Another idea is to use system identification. That is a concept from control. And the idea is so we wanted to see if this PD is a correct way to describe our MRE data. And why is it interesting? First, you can use it as a quality control. Let's say that the patient was moving a lot. So then it's so noisy that the data you acquire doesn't follow the expected PD, for example, or you can use this for filtering or even for inversion as well. So the idea is like this. So yeah, you have your raw data, and then the idea is to learn the governing equation PD. So then you just have some hypothesis. You say, my equation, my PD should contain these components, and then you do the method, and then it realizes that only these are the important ones. And then if these are the ones that you expected, then the data is good quality. So this is some results from Hampus with a phantom. So then it's just like they just put some inserts here, and then you would expect that this Laplacian component will be homogeneous, so everything will be the same color here. We found that it was kind of true, except for this insert that was a bit off. So we think that there was like maybe this insert was a bit loose or something, because it doesn't follow the theory. Yes, so that was the last slide. So then at KTH, we just try to develop new methods for answering clinical questions. And yeah, we're mostly focused on brain, but some members also work with breast and other stuff. Yes, and we are open to collaborate with others groups, of course. And this is our group.